Alright, so in this video, we're going to be looking at a mixing problem question. So the mixing problem questions are really not that hard. There's just kind of a cookie cutter kind of way to do these problems for the most part. But there's also a lot of basic understanding that you can develop to solve these problems. Here I have one of those problems. I had to attach these pictures like this. A tank contains 1,000 liters of brine. Let's first identify what brine is. Brine is basically salty water. I just want to put that out, in case it doesn't matter in the context of the problem. It will make sense, but it doesn't necessarily matter to solve the problem, but it's just kind of a fact. With 15 kilograms of dissolved salt, pure water enters the tank at a rate of 10 liters per minute. The solution is kept thoroughly mixed, and that's important. Right? It's thoroughly mixed, and that's something we usually assume in mixing problems, that the solution is being mixed and drains from the tank at the same rate. Okay, and that's also something typically you assume. You don't necessarily have to. Sometimes they could obviously give a different rate, but in most elementary problems that involve the mixing problems, we do have the same rate. How much? Because it doesn't matter on it doesn't make the problem a little bit more difficult or anything if you change the rate. So typically it's just kept the same rate. How much salt is in the tank after 10 minutes, after 20 minutes? So 20 is you have to plug it in. So this is typical question. So let's look at the function that I can identify for this problem. So if I say s of t, right, and this is gonna be equal to salt in tank after t minutes, right? So t minutes. So that's s of t. All right. So let's see how we can set this up now. So remember the basic kind of formula for this is as follows, right? So we want ds by dt. In this case, it's ds by dt because it's the rate at which we're looking at the rate at which we have this salty water, the salty water salt content is changing. So this is going to be equal to so this is going to be the rate in minus the rate out. So the rate in minus the rate out. Now, what do I mean by rate in minus the rate out? When I say rate, it's not just the rate at which the water is coming in or something. It means the rate at which the salt is coming in this case. So the rate in is actually, we can split this up into two portions, into two parts. This is going to be the rate at which the liquid is coming in multiplied by the concentration. So the concentration of salt, right, in this case, of salt. And then the rate out is going to be, of course, the rate. In this case, it's the same rate, so these two are equivalent, times the concentration of, again, the salt, right? And this is mostly the tricky part, the second one here. So let's try to. So this is kind of the cookie cutter kind of thing you can follow for these problems here. So let me box it in. Okay, now let's use our values. So ds, let me make this a little thicker. ds, yeah, that's good. ds by dt is going to be equal to, so what is the rate in? This is rate times the concentration. Well, rate is going to be, so let's see, pure water enters the tank at 10 liters per minute. So that's the rate, right? That's 10, okay? This is being multiplied by the concentration. This is pure water, so this is pure water, which means that the concentration of salt in that water that's being entered is going to be 0. That's something you need to know. So that's just minus, so we know what this is going to end up being. But then the rate out is the rate, same rate, which is still 10, right? The same rate. We underlined that before. And then in this case, we're gonna have we're not gonna have a pure water solution anymore, because the tank contained 15 kilograms of dissolved salt as to start with. So there is going to be some salt concentration, but that salt concentration is not going to be constant. It's going to be changing because we're entering pure water. So at first it's probably going to be a little bit more salty, and then over time it's going to be less and less salty. So that's a function, right? It's a function. So that's the salt, that's S of t. That's going to be the top, the numerator, the salt after t minutes. Then the concentration is how much salt is in the tank of a certain volume, and then that volume in this problem is going to be 1,000 liters, and that could vary, of course, in different problems. So that's 1,000. Okay, I'm not using units for this because this is not a physics problem or anything where you need to specify the units. You can specify the units, of course, and some people do. I think it kind of complicates things, but you can always specify. I also like to use like a unit analysis outside here, but you don't have to. So this is just going to be 0. And so this is ds by dt is equal to -10 times s of t over 1,000. And of course, you can include units. I did not, but you can for sure. This is going to be zeros will cancel. So ds by dt is equal to -s of t over 100. Okay, this is interesting now. Now what we have to do is we have to get the s's together and well, the t's together. We only have one t, so we'll get the constant to the t side. What we'll do is we'll just cross multiply for now. So this is just going to be 100 ds is equal to -s of t dt. We don't need to include s of t. We'll just say it's s instead of s of t, and then dt. It's the same thing, okay? Just it's more like a variable now. It looks more clean with our calculations. We can divide by 100 and divide by -s. So this is dividing by 100 on both sides, and then I guess we can multiply by 1 over. We can just do 1 over s. We don't have to do the negative in this time. So let's look at the calculations. So this just ends up being 1 over s ds is equal to -1 over 100. Am I doing this right? -1 over 100 dt. Now we can integrate both sides just as like that. This is going to be the natural log absolute value of s is equal to, this is negative 1 over 100 t plus the constant of integration. Let me write this neater. So this is going to be t plus the constant of integration. So let me double check to make sure my work is all correct. So -100 1 over 100 t. Yeah, this is right. Now we wanted a function, and we have this weird c now. We have a family of functions, but no, it's not a family of functions because we can use some given information to identify something, to identify the c, to get a single function that we can use to determine the salt after t minutes, this thing right here. So what's the given information? Well, the given information is at time 0, right, when there's no, there's no water being pumped in necessarily because it's time 0 at the moment in time, we will have just 15 kilograms of dissolved salt. So at this moment in time, we will have 15 kilograms of dissolved salt at time equals 0 in the solution. Okay, in the solution. Okay, so given that information, how does that help us? Well, and time 0, we're going to have 15. So this is going to be the natural log absolute value. We don't need the absolute value since it's already a positive number. Natural log 15 is equal to -1 over 100 times 0 plus c. C is equal to natural log absolute value of 15. That's our c value right there. Okay. Now that we know this, we can write that in place. So this is absolute value of s is equal to -1 over 100 t plus the natural log of 15. Now, what we can do is, since in this problem, let me scroll up, we wanted how much salt is in it after t minutes. So we technically do have it, right? Do have this function, but we can obviously simplify just to get it like a proper function and raise e, right? E raised to this is just ln. This is the absolute value of s is equal to e raised to -1 by 100 t plus the natural log of 15. Okay, so this is just the absolute value of s is equal to e raised to the negative 100t, negative 1 over 100t, times e raised to the natural log of 15. Why did I do this? Well, because the e and the natural log can cancel out, giving me just s absolute value is equal to e to the negative 100t times 15. I could have brought that 15 in front here. There. So just squeeze it in there. Remember, what's this going to be? Well, it's just 1 over e to the 100t. And this is just going to always be positive, so we don't need the absolute values. So that's just 15e to the negative 1 over 100t. This is your function. So s of t, we can say if we wanted to. Let me make some space for this. S of t. Let's get this here. Okay, s is s of t. So this is part A, right? This is part A right here. Satisfies part A. Let's do part B. So let me scroll up. Part B is saying, so we did part A. This was part A. And then part B is, what is it after 20 minutes? Well, this is just a simple problem, right? What is it after 20 minutes? Well, what is S of 20? What is S of 20? Well, that's just going to be 15 e to the negative 1 over 100 times 20. So this is going to be equal to 15 e to the negative 1 over 5, right? Let me see, 1 over 5. So this is just equal to 15 divided by 1 over e. So e to the negative 1 over 5 is 1 over e to the 1 over 5, which is 15 over e to the 1 over 5, or fifth root of e. So this is just fifth root of e, just like that. And this is equal to s of 20. And of course, in this case, I would like to specify units. That is going to be how much salt. So that's going to be in, let me see, 15 kilograms. So this is going to be in kilograms. And this is your answer for the second one. All right. Okay, so hopefully this problem wasn't hard. I should have utilized the space over here, but that's fine. Anyway, this is just the basic cookie cutter formula you would need to use for these kinds of problems. Use this cookie cutter formula and you'll be good for most of the problems that you'll encounter. Okay, so I will be making other videos on this as well, so stay tuned.